Hello and welcome to a delightful introduction to digital data for diligent dentists. I'm Dr. Shah and I'm the one that's administrating this CE course. Now let us get the disclosures out of the way. I am the owner and the primary developer of Clear.Dental, which is a dental EHR software suite. This CE program is being delivered without any commercial support. This CE activity is being jointly provided with CE Zoom Partners LLC. Members of the CE Zoom Planning Committee have no relevant financial relationship to disclose. Okay, let's review some basic rules about this course. First of all, this is just a basic overview of a number of topics that pertain to digital data. A lot of things in this course are oversimplified to make it easier for doctors to understand. If there is any interest, I can definitely go over any of the discussed topics more in depth. The colors that you see for each rectangle have no real meaning. It is there just to separate out the different ideas in each slide. Any image, unless you see the link address in the bottom of the screen, is taken from Wikipedia and is under the Creative Commons license. That, or it was made by me, which is under the same license. Now you're probably wondering about who I am. So, I graduated from Carnegie Mellon University back in 2006 in a degree in Information Systems, Human Computer Interaction, and Computer Science. From 2006 to 2010, I worked for Lockheed Martin, where I was making submarine sonar software, and I was also making video games for the Marines. I then worked for ICS back in 2011, where I was working on the MiGo project before it was canceled. I then did the most logical next thing in my life and became a dentist. I graduated from Tufts back in 2015. I've worked for a number of dental practices, public and private. In 2021, I started my own dental practice from scratch, Zen Family Dental, located in Ashland, Massachusetts. And now here is the overview for this course. First, we will go over what digital data actually is, along with a few definitions. Then, we're going to go over basic text like patient names, case notes, and even emojis, and see how they're actually stored on a computer. Then, we will go over how images like radiographs are digitally stored, and we will also review how you can enhance whatever radiograph you have stored. Then we will take a quick detour and review how the World Wide Web works and how HTML and servers play a role in it. Then we will go over 3D computer graphics along with the STL file format and how that relates to CAD/CAM. Then, at the very end, we will tie everything together and talk about deep learning and AI and how that relates to the actual digital data we've been talking about earlier. All right, now for part one, digital data. Now, if you go on Wikipedia and look up the definition of digital data, it'll give you a very long definition, which is the most accurate one. But since we're oversimplifying everything in this course, let me just say that digital data is simply representing data using a series of numbers or digits. And to oversimplify it even further, if you can represent something as a number, then it's pretty straightforward to digitalize it. If there is no clear way to represent something as a number, then it cannot be digitalized. Now, let's take a step back and really think about how we represent numbers. We really don't think about this, but what makes a number a number? It is a series of numeric digits. So, with our system, which mathematicians have called base 10, we start with the lowest value of digit 0, Then we work our way up until we no longer have a bigger digit. So we start with 0, then we do 1, 2, 3, and then all the way up to 9. We don't have a bigger number in a single digit than 9. So what do? We push the digit on the left hand, which is an implicit 0, to a 1. And then on the right hand side, that 9 becomes a 0, and now we have 10. We can repeat these steps to give us as many digits as we want to represent as big of an actual number that we need to represent. Now, to oversimplify computers, they're really a series of switches that are on or off, and thus they store everything as either a 0, which is off, or 1, which is on. But they use this binary system to count in their own way. So you start with 0, just like our base 10 system. They go to 1, just like our base 10 system. But now they're already at the maximum limit that their system provides. So then they go essentially to 10, which is our system of 2, and then and so on. So when you see 1, 0, 0, 0, it actually is 8. They call this base 2. Each 1 or 0 is called a bit. So if you have 4 bits, there are 4 ones or zeros. If you have 32 bits, you're talking about 32 ones or zeros. With more bits, you can represent a larger number. So the formula to calculate the total number of different values of an n-bit number that can give you is simply 2 to the power of n. Now, 0 does count as a number here. So if we want to calculate the range of an n-bit number, it is from 0 to 2 to the power of n minus 1. Now, we've only been talking about numbers here, but obviously computers can do a lot more than crunch numbers. And so the question becomes, how would you represent something that we don't normally associate as a number, like love, anger, fear, happiness? How do you get these types of concepts, or at least be able to represent such concepts on a computer? This is where Ada Lovelace comes in. She is the first software engineer ever. She was actually programming on a mechanical computer called a Babbage machine. Her original assignment was to write a way for this Babbage machine to calculate something called Bernoulli numbers, which, since this is a very oversimplified course, is just a complicated way to calculate very complex fractions. Her biggest contribution is this idea that numbers can represent more than just actual numbers. Numbers can represent certain ideas. Back then, she had the idea of using numbers to represent different notes and actually using such a mechanical machine to generate music. And so, going back to our previous example, I know it sounds like a cop-out, but essentially we take certain ideas and assign a value to it. So we would say love equals 0, happiness equals 1, and so on. And then you can actually store that information onto a computer. Now we are going to apply what we have learned so far into something relatively simple: text. So back in the 60s, a bunch of American computer scientists created a standard that we now know as the ASCII, but we just call it ASCII. This standard assigned different numbers to different letters. For example, capital A is the number 65, lowercase t is the number 116. Computers use this system to convert from numbers to text that we see on the screen and vice versa. For your own edification and experimentation, I've included two links that you can use which have an interactive site that you can type in different words, letters, and you can see how it gives you the actual numbers. So now let's look at this example of hello world. In this specific example, I'm using binary, but you can always convert that into our standard decimal system on your own. But do notice that space is a number because there's a number assigned for just the space. Same thing with the exclamation mark. That is a number as well. And using the ASCII standard, each letter has 8 bits. Therefore, in this very specific example, we have 96 bits of data. Now, because in ASCII each letter is 8 bits, we've decided to have another definition for data storage called bytes. By definition, 8 bits equals 1 byte. So back to this example, because we have 12 characters, including the space and exclamation mark, there are 12 bytes of data in Hello World. Now, as I mentioned earlier, ASCII was made as a American-centric standard. It did not account for any other languages outside of English. Therefore, much later, there was a new standard that was built on top of ASCII called Unicode that actually accounts for these different characters that are not in the normal English language. So in this example, you can see Jose with an accent over the E, and then Jose with no accent. It gives you very different numbers for that E because the one on the left side is actually using the Unicode standard for that E on the accent versus on the right side, it's just using the regular E. So although we consider the Jose on the left and the Jose to the right to be more or less equivalent, as far as computers are concerned, these are two very different names. So sometimes if you're doing a search on your own database or something like that, you may actually have to search for both Jose with the accent over the E or without the accent over the E, simply because computers see it as two very different names. Now, the Unicode standard did more than just extend the ASCII standard to other languages. It also allowed for these icon sets called emojis. You've probably noticed them on your phone. So one thing that you may have noticed in these examples is that there's more than just one byte for each emoji here. For example, in the molar example, it's 240, which is 1 byte, 159, 166, 183. So that's 4 bytes of data. Now, our hard drives, our SSDs, they are holding gigabytes, even terabytes of data. So it's not a huge problem in terms of data storage. However, when you're using something like text messages, it actually does take up more bytes because of that. And now for our next topic, which is digital images. To talk about images, first we have to talk about light. So, what is light? As we remember from physics, light is an electromagnetic impulse or radiation that comes at different frequencies. The light that we can normally see is in a very specific range of frequencies that we commonly call visible light. So anything in that spectrum we can actually see with our own naked eye. On a modern monitor screen, there is a combination of red, green, and blue lights that combine together to give us that full spectrum of visible light. What the monitor actually does is that it brightens or dims each red, green, or blue to create a new color. For example, if we want to show the color yellow, we would set red and green to be the maximum brightness, while blue is at the most dimmest. That way, it gives kind of that illusion of yellow because the red and the green are combined together. You normally don't see these individual pixels, so you actually don't notice the individual red, green, or blue when you're a couple feet away from the monitor. So it's more of an illusion that we can see multiple colors on a single screen. But before we get too ahead of ourselves, let's actually define what a pixel is. So a pixel is actually a shorthand for picture element. A pixel is part of a grid of colors that is used to make an image. Normally, each pixel is just one color, and then you lay out the pixels onto a grid, and that grid gives us that image. So each pixel normally has a red, green, and blue value. We tend to call each color in each pixel a channel. So for each pixel, we actually have three different values. In most, but not all systems, we have 8 bits for each pixel channel. So if we remember from our previous chapter, in an 8-bit system, the value can be between 0 and 255. With most systems, what we have decided is that 0 means make that channel as dim as possible, while 255 means make it as bright as possible, and you can use it any number in between 0 and 255. There's also another system, which we'll get to much later, but it's called a floating point system, where 0 means also make it as dim as possible, but 1.0 makes it as bright as possible. Now, let's see this in action. Here's an image of me doing the fluoride taste challenge. So we have a bunch of pixels all laid out in a grid to make a picture of me, but you don't normally see these individual pixels, so let's zoom in a little bit. This is a cool site you can use to analyze pictures down to the pixel level, and you actually can see for each pixel what the values are. So here is a slightly zoomed in version of the same photo, and even more zoomed in, and even further. And on the side, once we zoom in to a certain amount, it'll actually show how much red, green, and blue there is for each pixel. As you can notice that most of the pixels are very similar to each other. You normally don't have something that has drastic different pixel values when you are having such a high resolution photo. But in this specific area where I zoomed in, you can actually see the reflection of my glasses in the upper right corner there, in which it has a much higher green value and lower red and blue values compared to the rest of this grid. So you can use this for any image, and you can actually see pixel by pixel how much red, green, and blue there is. And as I mentioned earlier, this is 8 bits per channel. So each red, green, and blue will be a value between 0 and 255. So that's how it works in the visual spectrum with photographs essentially. But how does that apply to radiographs? So radiographs are a much higher frequency than we can actually see. But we use a similar sensor, this CMOS sensor, as we normally do in regular digital photography. It's just calibrated at a much higher frequency. So you still have the same idea of different values for each pixel, and then they are still transferred to the computer the same way as any other regular photograph, but they have to be translated in that from that frequency of radiology to the visible spectrum so we can actually see it with our own eyes. So how does it convert from the radiology space to the visible light space? Well, each system is a little bit different, but I'm going to go based on the standard FDA method of doing the conversion. So first, there's normally called a black image. A black image is a set of values in which the sensor itself detects the amount of radiation that is essentially background radiation, because no matter what, there's going to be a little bit of radiation in the atmosphere, in the patient's mouth, and so on. So that's called the black image. Then you have the exposure image. That's the time you actually put the sensor into the patient's mouth, get that x ray gun, and shoot it at the patient's mouth to get the full exposure. So the idea is that you don't want to have that background radiation affecting your image. So pixel by pixel, you actually subtract each value from the full exposure from the black image. And then that gives you the raw image, which is still more or less useless for humans to see. Why is that? It's because most CMOS sensors actually use 16 bits for each well that it detects radiation. And most monitors, as we talked about earlier, are only 8 bits per channel. So then we see just a bunch of grays. We can't really make out what it is showing. Here is a link to a website that takes in an image and then creates what's called a histogram of the different values for each pixel. So if you see a part of the graph that is high, that means a lot of pixels are that value. Now, here is a raw radiograph of a paperclip. You can barely make out the shape of the paperclip because the contrast is so terrible. Why is the contrast so terrible? Well, it's because all of the values that you see in that radiograph are in that in-between spot between 0 and 65536, which is 2 in the power of 16 minus 1. Um, because of the way that the monitor works, it just divides it by 2 in the power of 8 such that you only have a bunch of values near 127, 128. So you can barely make out anything, even though the data of the contrast is there. We just can't see it by default. The easy method to fix this is actually to stretch out that histogram, to zoom in where all the values, all the pixel values are close to each other, and just stretch it out to actually utilize this 16-bit space. So in this case, what I simply did was use simple what's called interpolation to say, okay, for these values, just divide it by this much, for this values, and multiply it by this much, so that way we use the full spectrum of the 16-bit. Therefore, when it gets translated to an 8-bit monitor, it's actually visible. Now let's go back to our byte weighting example. So we had the raw 16-bit values, which all had very similar values, and I stretched it out using interpolation, which gives us the center image. But something doesn't seem right here. You can see at the center of the bite wing, everything is white, but the teeth themselves are black. What's wrong here? Now, let's remember about how we normally represent values on a pixel. The higher the value, the brighter the color it is. That's more or less the standard. But for radiographs, it's actually the opposite way, where more exposure to the actual radiation makes it black, while less exposure to radiation, like teeth, enamel, and so on, makes it white. So, what do we do to fix this? Well, we just basically invert the values. So we basically say, okay, from one side of the spectrum, you just go to the opposite side. So if you're a 0, you're now 255, and vice versa. If you're a 255, you turn into a 0, and you do that for every pixel value. So to make it visible to other doctors, you actually have to invert the image such that most doctors can actually understand, okay, this is the bite wing that I need to see. And with all of those steps, you finally get the actual image that the radiograph shows you. Now, in this very specific example, please ignore the upper left and lower left corners. That is actually just due to the shape of the radiograph sensor to make it easier to fit into the patient's mouth. Most software actually blacken them out, but I'm just being lazy here and just letting the junk pixels stay in the image. So now that you have the actual radiograph, what can you do with it? So one thing you can do is brighten it up. But what does brightening up an image do? Well, what it does essentially is increase the value of each pixel. When you increase the value of each pixel, it only does a certain amount of increase. So if the value was 0 and you increase the brightness by, let's say, 5, it goes from 0 to 5. If it was previously 100, then it becomes 105. That doesn't sound so useful at first until you're in a situation where you have two dark areas and you want to be able to differentiate those two areas. Brightening it up will makes it easier for your eyes to be able to differentiate between those two regions. Of course, if you brighten it up too much, then the whole image becomes white. The other thing you can do with an image is increase the contrast. Now, what contrast does is that it makes the darker areas further darker and the brighter areas even further brighter. This is useful if you want to be able to differentiate certain gray areas. A lot of times you actually want to combine brightness and contrast. That way you can actually first shift the brightness to a certain level and then increase the contrast combined with both. If there's anything that you want to see and be able to differentiate, let's say an interproximal area, that can be helpful in actually seeing it with your own two eyes. There is another effect that is often used called the unsharpened mask. Often you'll actually just see it as the sharpen filter. What it essentially does is take the original image and actually blur it first. So think of blurring as essentially smudging it. And then they actually subtract the two values between the blurred image and the original image, and then output that as a new image. By doing that, you tend to remove any kind of pixels that are very close in value and then really highlight the differences in pixel values. So in situations where you want to actually see anything like a lesion or something that has very subtle pixel differences, sharpening it up using the unsharpened mask can be very useful. So back to our example, here is the before image. And this is after using the unsharpened mask. Now, as for actually storing these radiographs onto your computer, there's plenty of different formats out there. But just to very generalize two different aspects of storing the images, the first common way to store the image is a lossless compression-based image storage. Now, what is compression? Don't worry too much about it, but the idea of a lossless compression is that nothing is ever lost. The pixels that are saved are the actual pixels that were in the original image. A lossless image tends to be a little bit larger in size compared to a lossy image. But in modern times, with the size of radiographs and the amount of storage we have, it's not that much bigger. Contrast that to a lossy image. So there is something called quantization, which you don't have to worry too much about, but based on the amount of quantization, you can lose certain details that were in the original image. So in this example, I actually really compressed the right side image. And you can see a lot of artifacts, a lot of what's called banding, kind of those waves you see in each tooth that wasn't in the original image. Those are known as JPEG artifacts. So if you ever do store your images and you have the ability to say which format, try to save everything in a lossless format versus a lossy format. Yes, it is going to be bigger when you store it as PNG files, but I think the benefits of having each pixel preserved outweighs the cost of the file size. Now, to make things even more confusing, there is the compression formats that we know about, like PNG and JPEG, but there are what's called container formats, in which there is additional information about the image that's stored into the file. A common one you see in dentistry and medicine is called DICOM. So in a DICOM, for each image, there's additional information about that image. Like, for example, was it on the patient's left side, right side? The DICOM file also has information like the patient's name, date of birth, sometimes the doctor's information as well. So you get a lot more from a DICOM file. But that's just a container format. That doesn't say anything about the compression format or the compression algorithm that is in each DICOM image. And that's the reason why when you have a DICOM file, it can hold multiple images. There is another format also known as TIFF, but we like to joke that it stands for thousands of incompatible file formats. So what is inside a TIFF could be lossy, lossless. You don't really know. There's actually lots of different ways an image can be stored in a TIFF. But for whatever reason, a lot of software out there actually stores it in a TIFF. But I would recommend against that simply because you don't know the quality of the radiograph that you're getting when you store as a TIFF or send it out as a TIFF. And more as an FYI, a digital video is really just a bunch of images put together and shown in a very fast frame rate. Very similar to like a flip book. So you see an image, it replaces it really quickly and gives you that illusion of motion. And speaking of cool videos in motion, let's now talk about the World Wide Web. Now, technically speaking, the internet and the World Wide Web are two different things. So, first let's go over the internet. To oversimplify it, the internet are simply just a bunch of computers, clients, and servers connected together in one giant network. The World Wide Web is actually a more recent invention by Tim Berners-Lee in 1991, but World Wide Web, as we understand it, is actually a collection of different standards and technologies like HTTP and URL and HTML. So HTTP, which stands for Hypertext Transfer Protocol, is a standard way for a client, like on your laptop or cell phone, to request a web page that a server holds. So you can see on the right-hand side, this is a request to example.com, and it's saying a little bit about what type of device you're using. And then the server responds back with the example page. There's, of course, at the very top a header to say, yes, you made a valid request, and here is the response. Now, how does a computer know where to send the requests to? And how does a server know where to send its response to? So each computer has an address, which we often use the term IP address for. And for each device that's connected to the internet or to a network has an IP address. And just like everything else, it's a series of numbers. In this example, we're using IP version 4, in which there are 32 bits representing the IP address. Most commonly, we actually use 8 bits 4 times, and we use the period to separate each of those 4 numbers. So in this example, 172.16.254.1. And that's the address in which you are actually assigned for that network. So this system works for both a local network and for the internet. How they all relate and all that, that's kind of beyond the scope of the CE course. But the main thing to know is that this IP address works very similar to like a phone number. But this is kind of news to you, most likely, because when you want to go to a place like Google.com or Amazon, you don't actually type in the IP address for those websites. You normally type in something like Google.com or Amazon.com. You're not typing in 142.251.32.11. I mean, it would be extremely difficult to remember the IP address of every website that you want to go to, even if you had it bookmarked. And that is where domain names come in. So whenever you want to go to some place like google.com, it actually asks a special server called a DNS server. Hey, I want to go to google.com. What is the IP address for google.com? So the domain name server, which is normally provided by your ISP, like for example Comcast or Xfinity or Verizon, they provide that domain name server. And they'll respond back, oh, it's in this case 142.251.32.110. And then your computer says, okay, I know what IP address is. And then we'll automatically go to that IP address and say, hey, give me your homepage or whichever specific URL that you are requesting. So, how does one get a domain name? So the first thing you need to do to get a domain name is have it registered by a registrar. These registrars then actually submit to a universal database that's used by all these different ISPs to use on their own domain name servers. So that way, if you register with a certified registrar, then everybody in the entire world can actually associate the domain name with the IP address of whatever website that you have. So, where this actually plays into dentistry is actually having your own website for your own practice. Now, most domain names end with a .com. That's known as a TLD, top level domain. So, if you go to Amazon.com, the .com signifies that this is for a commercial entity. .edu is for .educational entity, and .org is normally reserved for nonprofits. Now, how strict are these TLDs in terms of saying .com is only for commercial? They're not that strict. This is just for informational purposes rather than a strict guideline. There happens to be a .dental TLD. I would actually advise against that, mostly because a lot of email software and also other software that verifies URLs don't understand the .dental TLD, only .com, .org, and so on. So, yes, there is a .dental TLD. I got a few websites that have a .dental TLD, and it's been nothing but a headache. Now, something you probably hear as a requirement for your website is that it needs to be encrypted. What does that mean? So in the old days, every web page and request for a web page were in plain text. But that was a problem. You see, when you connect to a computer on the internet, it's extremely rare for your laptop or cell phone to actually directly connect to the server that you're requesting. It actually goes through a number of other computers in order to actually reach its destination. The further away you are in the network from the server, the more hops that your request needs to make in order to reach its destination. Kind of like if you were to send a package from New York to LA, it's probably going to go through a couple distribution hubs before it reaches that final destination. Now, with plain text, it's like having a transparent package. Sure, not everybody is looking at it, but it does allow anybody who wants to take a look at it see what's actually inside the package. That could be a problem if something inside that package is like medical records that you don't want the entire world to see. So, with plain text, somebody, we often call a man in the middle, can listen in to both the request and to the response, which is something we really don't want to do with medical records. So I won't go too heavily on the math, but the basic idea is that both the client and the server uses very sophisticated encryption algorithms to be able to send both the request and the server gives the response. The person in the middle cannot read it because it just looks like gibberish. The idea is that there's a way for both the client and the server to communicate where only those two know how to communicate with each other. So you probably notice when you're browsing the web, right next to the URL of the website that you are browsing, there's sometimes a lock right next to it. When you see the lock, that means it's using the encryption to communicate with that website. If you don't see a lock, or if they show a lock with the cross, like in the lower example, that means everything is being sent and received in plain text, and anybody can listen in to the conversation that you're having with that web server. So, to enable encryption for your website, you need to use a certificate authority that allows you to encrypt data from and to your website. Here is a list of certificate authorities that are available. I am slightly biased towards Let's Encrypt, mostly because it's free. Now let's go over a topic that's very dear to me, which is computer graphics in 3D. But before that, there are two very important topics that we have to cover. First, over matrices and over floating point numbers. So, what is the matrix? As you probably remember back in middle school or high school, it's simply a way to hold a bunch of numbers together. There are certain operations you can use with a matrix along with a vector to do some interesting math. Something to keep in mind is that when you're using vectors and matrices and you're multiplying with each other, it gives you a result that requires not only a lot of multiplication, but a lot of independent multiplication. So in this specific example, the first row doesn't depend on the calculation from the second row or the third row. So each of those multiplication can be done basically at the same time. Now, a floating point number is really similar to the scientific notation that we used in chemistry, where there's two parts. There's the significand, which this first case is 1.53, and then you have an exponent, so it's 10 to the power of 15. So you can use this to represent really large or really small numbers without having to write out a lot of zeros. How the computer exactly represents that is not too important, but just like everything else on a computer, it's represented using just ones and zeros. So in this specific case, there are 32 bits that are used to represent a floating point number. And if you combine them together, you can get a decimal number. However, you cannot represent certain values like 0.3 very precisely due to the way that floating point numbers work. Another thing to keep in mind is that these floating point numbers require a lot more computational power to do things like add, subtract, multiply, and divide compared to regular integers that we've been talking about earlier. And this is where GPUs, which stand for graphical processing units, come in. They are specifically made to handle these kind of floating point numbers and their operations. As a matter of fact, they tend to be orders of magnitude faster than their contemporary CPUs, central processing units. This chart is slightly outdated, but it shows how large of a performance gap there is. And just in case you were wondering, the major CPU vendors include Intel with their Core processors and AMD with their Ryzen processors. The major GPU vendors also include Intel with their Arc GPUs. That's not nearly as popular. Then there's AMD with their Radeon GPUs. And most famously, there's NVIDIA with their GeForce and RTX line. So, why were GPUs designed to handle floating point numbers so quickly? It's because a lot of the data in 3D computer graphics and video games is stored as floating point numbers. When you are playing a 3D video game, you want the screen to update as fast as possible. You can't wait forever for each frame to be calculated. Moving and transforming 3D objects requires a lot of the same matrix and vector math we were going over earlier. The faster the GPU, the more objects it can move and transform each second, and therefore the better the graphics. As time went on, people demanded better and better graphics from their GPUs. Therefore, GPUs got better and better graphics, and in return, it got better and better at doing this floating point number math. So, in the present day, they are really, really good in handling lots of floating point numbers. How floating point numbers are relevant will come up later, but for now, let's just talk a minute about 3D graphics. One basic idea to keep in mind is that, in general, all 3D objects are made out of triangles. For fast graphics on a GPU, having everything made up of triangles is the fastest way to do all the calculations needed to show the 3D objects on the screen. Therefore, in computer graphics, there is no such thing as an actual curve that can be rendered onto a GPU. In this example, it looks like a perfect sphere. However, when you zoom in, you can see the individual triangles. And whenever you're doing CAD/CAM, sometimes the software will talk about normals. All you really have to know is that normals are calculated just to figure out what is in the inside of the object versus the outside of the object. Normally, the software that is generating the actual triangles will calculate the normals for you. Now, when you read an STL file, what it really is just a series of triangles that generate the object. So this particular STL file, I've actually decoded it as a regular ASCII form so you can actually see what each surface looks like. So let's start from the very beginning. You can see that it first says what is the normal, so it's pointing that is the outside vector, and then it has 3 vertices. Now, as I said earlier, everything is made up of triangles, and triangles has 3 vertices. So these are 3 floating point numbers for each vertices. The reason why there are 3 floating point numbers for each vertex is because there's an x, y, and z value. So whenever you're using a scanner like an iTero, it actually generates these triangles that are then rendered by your GPU. When you have a bunch of triangles put together, we often call it a mesh. .ply files are very similar to .stl files, with the only difference is that with ply files, they also have a color aspect to them. And as I mentioned earlier, there's then a red, green, and blue element for each triangle that is actually being rendered by the GPU. And now for the real reason why you're taking this course, AI, also known as artificial intelligence. So there's a famous quote from Arthur C. Clarke, which is, "Any sufficiently advanced technology is indistinguishable from magic." What I want to do is be like that magician that reveals their secrets. Although a lot of what I go over will not be enough for you to do everything on your own, hopefully by the end of this course, you will no longer see AI as simply magic. One of the problems in talking about AI is that there are so many different types of AIs out there. For example, there is software out there that checks if you have a bite wing or PA radiograph as an attachment before sending out that claim for the crown. As a disclosure, I actually wrote software that checks if the patient had a D0150 in the last 5 years, and if they did, it would automatically switch them over to a D0120. Things like giving roadmap directions, like Google Maps, was considered to be AI for decades. There's other types of AI out there, like, for example, the AI that you play against in chess or you play against in video games. That doesn't use the same kind of AI you'd normally see in a neural network, but it actually uses something slightly different, but it's been around for decades. This more neural network or deep learning AI has been around for many decades, but it hasn't gained that much popularity until the last 5, 6 years, thanks to ChatGPT and other deep learning and other types of software that's now ready available for all people to start using. So back to my own bias, the old and existing AI is still important, but most people these days are more interested in neural networks for AI. So let's talk about the very basics of machine learning, also known as deep learning. First, you have an input. Of course, just like everything else in computers, it is a number. Then you have weights between the input and the output. The output is also a number. And of course, the weights in between are also numbers. So let's go over the basic steps in a very high level. So the first step is to fill out these weights with literally random numbers. That gives you the initial model. Then you test out this model by multiplying the number from the input to each of the weights that's in the middle. Each of these weights, actually their nodes, will then in turn send these results to the next layer of weights. It goes on and on and on until you get that final number at the right-hand side. When you are training, you know both the input number and what you expect as the output. So because we're starting off with literally random numbers for the weights, you can't expect your output number to be what it is supposed to be. So the difference between what you got out from your current model versus what you expect is often called loss. So what do we want to do? We want to minimize this loss. So we change the weights that are in the middle based on how much of a loss that we got. So if we have a huge amount of loss, we want to correct these weights by a large amount, and vice versa. So in theory, if we keep on repeating this step, we should get a very small loss and a very accurate model. Then we use another dataset called the testing dataset. This is a little bit different because we're not here to calculate the loss and then put that back into the model. We're just here to see how good that model is. So we normally use something like real-world data or some funny test cases that we want to see how the model works with. Then at the very final step is inference. This is when you are ready to show this model to the entire world, and the basic idea is that somebody is going to be putting in these input numbers and the model will just give out the output numbers. There's no additional training. You're just trying to get from input to output. That is it. So let's start off with a very easy example. So let's say I showed you this table. When I started with number 1, I get 2, and then if I start off with 2, I get 4, and so on. What do you think this model looks like when it's accurate? You can probably guess that all it's really doing is multiplying the input by 2 in order to get the output. That's how we as humans would look at this pattern to get that result. Now, let's see how you would do the exact same thing, but using machine learning. So because I already know this is going to require a very simple model, I'm just going to have just one node in between the input and the output. So you can see in the input on the left side being 4.0. Because I was mentioning earlier, everything tends to be this floating point number, so the 0.0 means that it could be a decimal. It could be 4.5 or 7.2 or 10 to the power of 16. Any of those are valid numbers. But anyway, we have the input. We have something that we need to multiply it with to get the expected result. So let's just say that the computer randomly picked 1.0 as the initial weight. So we go through the process. We take 4.0, we multiply it by 1.0, and then it gives us the output of 4.0. The expected value, based on our training data, is 8. Therefore, we have a pretty big loss, so we need to increase this hidden node. Excuse me, I meant to say increase the weight of this node. Now, how much you increase whichever node you have really depends on the situation, and it's more of the person that's doing the training to figure out how much a node should be increased and decreased based on the loss. So it's almost like an art along with the science, exactly how much you should fine-tune each node. But let's just say in this example, we only increase it by 0.5. So we go through this process again. We take 4.0, multiply it by 1.5. That gets us 6.0, which is still shorter of 8, but at least we know we're going in the right direction. So now we increase the weight to 2.0. So once again, take 4.0, multiply that by 2.0, and guess what? We got 8.0. No loss. Now, at this point, because there's no more loss, there's not too much that we need to do. We'd still have to go through the entire training data set, but in this specific case, we know we have the correct answer for this weight, and that's basically it. Most of the AI tools out there want developers to write their code in a programming language called Python. Here is the code that basically does the exact same thing we did together in the last few slides, but of course in Python. This is a very simple example, so you can expect for more complex model to be a lot more Python code needed to create those complex models. In this example, I'm using a framework called PyTorch, but I did not have to use PyTorch for making this example. It's just the one that I chose to do. So if you were to run this Python code onto your own computer, the output would look something like this, but not exactly like this. Why? Because that very first step was to assign a random value for the weight. So in this very specific case, that random weight was 0.367, which came as a huge loss. So, of course, you have to increase the weight until it gets to the right number. And in this example, it took about 100 loops to go through the model to correct itself to get a pretty accurate model with the weight being 2.0. Something to keep in mind is that everything is once again using floating point numbers. So things are not going to be super accurate. One funny thing is that you can actually look at the 50th iteration where the weight looks like it's 2.0, but then you look at the loss and it's still inaccurate. Why is that? Well, as I mentioned before, when you're using floating point numbers, the precision can be a little bit tricky. So there, even though the computer displays as 2.0, it's not really 2.0. It could be 2.0 plus a little bit extra that you don't really see. So that's why you have a loss, even though it looks like it's the correct weight. But the loss is so minor that we can more or less ignore it. Now, did it really have to go through 100 iterations to get me that accurate number? It didn't really have to. I just decided with my software to do 100 iterations. I probably could have stopped around 70 or 80 or even earlier. If even that 50 loop counter mark, I probably would have gotten a good enough model. But that's more of the developer of the AI to decide how good is good enough for the model for training. And then you can see the final test at the very end where I give the input of 5 and it gives me more or less exactly 10.000. So we know the model is good. As I mentioned earlier, I did not have to use PyTorch to develop that software. I could have used TensorFlow, I could have used Keras. There's plenty of other frameworks out there. And not all frameworks does the same steps when it comes to machine learning. There are some software that's specifically for developing the model, for training it. There is software out there or frameworks out there that's specifically for that inference step. So each type of software will do things a little bit different, and they all have different features that some developers like, some developers don't like. So a lot of times there is a lot of bias in terms of developer preferences. Some developers really like Python, some developers hate Python. They want to use something in something like Lisp or C++. So there is no shortage of choices when it comes to AI development tools. Now, let's go back and take another look at this chart again. Notice how for each vertical layer, each weight is calculated independently of each other. So the calculation at the node at the very top of the layer does not need to see the results of the calculation at the bottom of that same layer. On top of that, most of the numbers in this scenario are floating point numbers. You should be getting some deja vu here because we talked about these same exact requirements when it comes to 3D computer graphics. So what has happened in the last decade is that GPU manufacturers have created a way for developers to use the GPU to do other things besides showing polygons on screen. They are used to calculate these floating point numbers that are independent of each other, and since GPUs are much faster at this than CPUs, they actually do this AI a lot faster. This is the reason why many people are using GPUs to do the AI and not their CPUs. It's also the reason why companies like NVIDIA, which were previously known for computer graphics, is one of the major players in the AI market right now. But NVIDIA is not the only player in this game. There are plenty of different manufacturers and different types of processors that can be used for AI, either for the training part or for the inference part. So let's go over the CPU. Now, every computer out there, including smartphone, tablet, has some kind of CPU. And almost every kind of CPU out there can do this kind of AI. It's just that it would be very, very slow. It's kind of nice in that if it's something very simple, at least you have something to fall back on. And most of these frameworks that I've talked about, including TensorFlow and PyTorch, have a way to run everything on the CPU without needing any kind of specialized hardware. The next one I want to go over is CUDA. Now, CUDA was made by NVIDIA, and it's made specifically to work on NVIDIA hardware. It's been out since the mid 2000s, so it has a very long and rich history, and it has lots of support from NVIDIA themselves, and it's extremely popular among developers. Almost every AI framework that I have used has some way to connect via CUDA to an NVIDIA GPU or a any kind of AI accelerator card that they are now selling. They're now using a new brand called RTX, which is more for professional level AI training. The next one to go over is Rock M. Now, that is similar to CUDA in that it was made by one company, in this case AMD, and it's made to work with AMD hardware. The big problem with Rock M is that, one, it only works on AMD hardware, but two, it only works on certain kinds of AMD hardware, um, more of their higher end professional grade hardware than something you'd normally see on a laptop. The next one is called Metal. Now, Apple made the Metal API to work on Apple computers. So we're talking about MacBooks. It even works on iPhones, iPads, both their laptops and their desktop. The Metal is more of a catch-all term because Metal includes both their AI tools and also for graphical rendering because there's a lot of overlap between the two. So Metal is great in that if you have an Apple device in the last 10 years, it more or less supports Metal in some extent. So it's great in that aspect, but it only works on Apple devices, not on something like an Android or a Windows PC. The next one over is called Vulkan, which is also more geared towards computer graphics. But Vulkan does have the ability through their compute shaders to do some AI work. However, it is not that popular. The only framework that I know that uses Vulkan properly is PyTorch, which is more of an experimental version of PyTorch. It's not 100% supported. And one other framework called NCNN, which is specifically for CNN networks, but it will only use it for inference. It won't use it for training. And then the last one is One API, which is made by Intel. The nice thing is that it works on both their CPUs. So Intel and AMD make CPUs, and Intel have more recently been making GPUs, and they recommend using this one API to work with their GPUs. Now, technically speaking, one API could, in theory, work on other hardware like AMD and NVIDIA hardware, but as of right now, that support is fairly low, so you will not see too much software out there that's going to be taking advantage of one API, but anything can happen in the next 5 years, so I don't want to say that's going to be true forever. Now let's circle back to the very beginning of this course, in which we said if you can represent something as a number, it can be digitalized. If you can't represent something as a number, it can't be digitalized. And the same thing holds true for AI. If you have the ability to represent something as a number, then making it as part of an AI model is straightforward. If you cannot conceptually come up with a way to get something as a number, then it's a very difficult AI problem to have. So the reason why I spent so much time going over digital data is because it would then make sense on how these kinds of information would get in as input to the AI and then would generate that output. So let's go back to digital images. So how would you feed an image to an AI? Well, the AI will only see a bunch of inputs, which are numbers. So let's go back to a color image. You have these red, green, blue values, which is a number between 0 and 255. Sometimes you actually use a number between 0 and 1 as a floating point, just like I alluded to earlier. But it depends on how you want to do your calculations. There is no right answer, or always consistent answer on how you want to convert an image for AI. But at the end of the day, you need to give that AI values. And the way you give the AI a bunch of numbers is by giving it the individual pixel values. So you might be seeing some new AI models coming out of there that works on 3D models. But what is it actually doing? Well, it's looking at each vertex, each normal, and using that to feed into the AI model to give you that result. As I said, everything is a number. So, because STL and PLY files are a series of numbers or a series of digits, that can be fairly easily fed into a model. The only thing to keep in mind is that something like a model that's used in dentistry has a lot of numbers. So that means there's a lot of input. So it's not something that you can easily make in just a single day to say, okay, show me where the caries is in this 3D model. It takes a lot of data and a lot of processing power to do so. But that's a 2024 problem. It could become an easy problem an easy problem to fix in the future. But that's essentially the idea of how something like a 3D model or a 3D scan would be fed into an AI. Now, I didn't want to spend an entire section for this, so I'm just going to briefly go over this. But time can be represented as a number. The official Unix time that a lot of systems use is actually the number of milliseconds since January 1st, 1970. So if we have August 14th, 2024 at that specific time, you can convert it to the Unix time of 17236787112, and that gives you a number. So you can actually set as your input a bunch of time or timestamps into the AI. And as we talked about earlier, text is really a series of numbers as well. So somebody's name or your case note can be converted to a series of numbers as well. Now, remember how we did this kind of cop-out where we simply assigned different concepts to numbers? So, for example, love equals 0, happiness equals 1. Well, this is actually quite important when it comes to AI. So I applied that same concept into periodontal diagnosis where I assigned no gingival inflammation or healthy periodontium as 0, slight gingivitis as 1, and so on. So this is the easy way to make these kinds of assignments because you have to remember that either the input or the output, it has to be a number. So if you want to create something that gives you a diagnosis, it has to be a number as well. Of course, it becomes a little bit more complicated because what if the model gives you something like 1.5? Is that something in between gingivitis and moderate gingivitis? But what if we just set these labels in a more random order? It becomes a lot more of a trickier situation, and that's why having different categories sounds like a great solution at first, but it can get really tricky when you actually have different types of diagnosis, and it's not that easy to assign them as an individual number. Now, you don't need just one single input source. Technically speaking, an AI model can have different sources combined together to give you any kind of output. So I'm just going to give this as an example. So on the left side, we have your input, also known as independent variables, which is, yes, very similar to statistics. They also call them features. So features are aspects of the input. They call it sometimes shape because you can say, okay, I have 5, 6 different inputs. So the shape has a particular kind of set of values to say, okay, I'm looking at an image of this many pixels by this many pixels. So the model knows where to put all these different values. So in this hypothetical example, I put how many no-shows the patient had, what's the copay of the procedure, if the patient confirmed the appointment or not. So in this kind of case, if the patient confirmed the appointment or not, that's called a Boolean value. So it's either a 0, which means they didn't confirm, and 1 if they did confirm. So we use those extreme values of 0, zero point 0, and 1.0 to kind of signify these like true or false. And yes, technically computers are doing everything in binary, but in this specific case, it's either a 0 or a 1. And then we also put in miles away from the clinic, and we feed that into the model, and we can then come up with a percentage chance that the patient will show up. So if you are running your own private practice, you kind of have a model already inside your head that takes all these factors into account, and then you can probably calculate for yourself what the percentage chance that the patient will show up to their appointment. But the idea here is that you're taking variables from different locations and combining it to a single model. The model will do whichever math and then give you the results. A lot of people like to joke that deep learning and machine learning is really just statistics. And in many ways, that's true because at the end of the day, you're just coming up with different probabilities or likelihoods of the results. Now let's talk about LLMs. The most popular one out there is ChatGPT. In general, a large language model takes in a lot of words, sentences, pages, books upon books as its dataset to train with, and uses that dataset to create predictions of the next sentence or paragraph. Now, this is a oversimplification because it doesn't just look at the input that you type in to predict the next word. It actually has to parse in what you typed in and find the key words in its own model in order to give you something that looks like a proper answer to the question you ask it. But in general, it's still using the same kind of technology where you have different weights with different values. And what the AI here does is actually pick the one of the highest value to say this is the next word or this is the next sentence and so on. So in this example, you say you should brush your teeth using, well, it's most likely going to be toothpaste. Why? Because when it looks at brushing your teeth, it often sees the word toothpaste, and so it has a lot of association between these key words. So it just has a really high value. The funny thing is that you normally don't see in the interfaces that you see in OpenAI and other vendors out there is the ability to kind of fine tune that. To do that, you would actually have to write software that would say, okay, show me some other alternatives. Or sometimes they give you the option to give me the answer once again, in which case it will go through some of the different nodes, not just the highest one. So in this case, it could actually say Colgate because a lot of people say brush your teeth with Colgate. But these are, of course, made up values. I'm just using this for an example. So you might be hearing the term AI hallucination a lot. So let's go over how that can happen. So let's say in this made up example, I ask the AI, who is the best soccer player of all time? Now, we are relying on what the LLM is actually using as its training set. So, is it using a bunch of YouTube videos? Is it using, let's say, ESPN? It all depends on where it gets its data from. So let's say it's going on some joke website and it associates the best soccer player of all time as Scott Sterling. who is actually a fictional soccer player, but a lot of people like to joke that he's the best goalie of all time. But if the AI has that association, I mean, AI doesn't understand jokes. As I said, it's all about numbers. You can't really tell the AI, hey, this is a joke. It'll just see those two words associated. Best soccer player, Scott Sterling, and be able to connect the two and then give you the result saying Scott Sterling is the best soccer player of all time. So we normally call that hallucination simply because it just made up that answer, but it's not always completely made up. It's just giving whatever results it sees as an associated answer. So a lot of times it will confidently tell you something wrong. It's not completely out of nowhere. So yes, it is kind of similar to hallucination that it's made up, but at the same time, it's not completely made up. That data came from somewhere. So it's always important to know where the LLM is being trained, how it's being trained, before you rely it for anything important. Because of the popularity of ChatGPT, you are starting to see a lot more vendors out there providing models for you to download yourself. So, one way you can use something like ChatGPT or any other LLM is to connect it via the cloud model, where your computer connects to the internet, connects to OpenAI server, and OpenAI servers will actually take your input and put it into their model and just send you back the results. However, that's just one way of doing it. There is a way for you to actually download the model yourself onto your computer, and then you can actually put in whatever prompt you want to put in into that model, and then we'll give you that output. That means that if you run things locally, not only are you not relying on some other website to give you the service, but it will even work even when you don't have internet. So here's an example of me actually running a LLM locally on my own desktop PC. So I give it a prompt and it gives me the result back and even tells me how fast it actually gave me the results. And in this specific case, it was actually using the API Vulkan, which uses my own GPU to give me the results. So how exactly did that work? Well, first I downloaded the model from Meta. So Meta is the one that's giving out the Llama 3 models. But when I say models, that means all the different weights. So I store them on my own computer, and then I use a program called Llama CPP, which will take that model and my prompt and use Vulkan, which I said is not that commonly used, but in this case, Llama CPP can actually use Vulkan and use my GPU. In this case, it's an AMD GPU to give me that output. So yes, NVIDIA cards and CUDA is very commonly used for these LLMs, but they don't have to be used. There are other vendors, there are other players in the AI space. So let's talk about image upscaling. In general, image upscaling means that you have a small image. Let's say it's 100 pixels across and in height, and you want to make it bigger. So let's say 200 pixels in width and height. How would you go about it? So the traditional way to do that would be to just double for each dimension whatever value. So if you just had one black pixel at the top left corner and you double the size, you would then make it four black pixels. And you would actually apply on your new image that same kind of transformation. A lot of times when you use these kind of traditional methods, you don't really get any new information because you're just taking information from the old image and just applying to the new image. There's different types of filtering, like bilinear filtering, and there's other ways to make the image look a little bit better when you scale it a little bit higher. But at the end of the day, you're only using the previous image to make the new image. A hot new thing that's been coming out recently is using an AI image upscaler. So instead of just using just one image to make the new image. You actually have an entire model that looks at the surrounding pixels to actually guess what that new pixel value should be. So let's review this example. At the top there is a very low resolution image that I just used traditional scaling methods. So if you look closely at the letters, you can see there's a lot of artifacts. Some of it is related to the JPEG artifacts I was alluding to earlier. So it doesn't look that clean when I resize that image. Now, the image in the bottom, instead of just using the original image, it actually uses a large model to fill in all the missing pixels. The name of the software is Upscaler. You can download for free, but that's what I used to make that bottom image. Is it perfect? No. At the end of the day, all these neural networks do is come up with the best guess, and it did a pretty decent job. Most people won't see the weirdness of the fonts or anything like that, so I'd say it's good enough for most uses. So it could be a very useful tool for things like regular photographs. However, once again, we always have to take into account on how the model was trained, where it got its data from, and so on. So a lot of models use English because, well, the internet is full of English letters and people writing in English and even signs being in English. So if you throw in something that's a completely different language, it looks a little bit off. Now, it's not very clear that in this case, like, why is it off? But I can assure you in Gujarati, it looks kind of strange, but I guess in this case, it's good enough as well. This is actually a picture of my grandfather, and you can see there were a lot of JPEG artifacts, which it was able to clean up. But in doing so, when it's trying to fill in all those pixels, you can see some of the areas where the chin is, it doesn't look exactly right. Why? It's because this model hasn't been trained with my grandfather's face. It's not going to have all that data there. Now, if I were to make a custom AI and train it with pictures of my grandfather, it probably would do a better job, but that would be a lot of work. But don't expect an upscaler to work for every scenario. So, some doctors have been thinking about using an upscaler, an AI upscaler, for radiographs, which at first sounds like a good idea because then you can zoom in to the DEJ and actually see some more detail. However, I have found it not to be very useful. So let's take a look at this bite wing. I've zoomed in a little bit, and you can see there's not that much detail already when you're comparing to two, even though I zoomed in a fair amount. So let's zoom in even closer, and you can see the original on the left, the AI upscaled image on the right, and it doesn't seem like it's getting all that new data or anything out of the original image that we couldn't have seen already. And as I said, it's probably hasn't been trained with that many array graphs, so is it really giving you new data that was there in the first place? Is it really enhancing anything? I would say no, because at the end of the day, those new pixels are is based on other images pixels, not necessarily that original one. So there are other ways to enhance the original radiograph to make it easier to view. As I was talking about earlier, you can use an unsharpened mask, you can use whatever brightness and contrast. That can help you out in diagnosing your caries, but using an upscaler is probably not the best way to go about getting additional detail from a radiograph. So now let's go over AI caries detection. Now, there's been two overall ways to do automatic caries detection. The first method is more of a heuristic model. So back in the 2000s and early 2010s, one way to do the caries detection is more of a heuristic model where you look at certain dark spots, you look at the white spots, you make certain assumptions on where the teeth are, and especially in that bite wing, you can have a better idea of where the teeth are supposed to be. Go into the interproximal space and then mark the dark spaces the dark pixels that are in the interproximal space where the teeth are as caries or incipient caries, depending on how sensitive you want to make your software. There's been a number of papers on this, and of course, as a disclaimer, this is what I wrote back when I was a dental student at Tufts. There's a newer way of doing this, which is the deep learning method. Two big players is Overjet and Pearl, and there are new ones coming in every year. Now let's go over how caries detection is done via deep learning. Every company out there that does automatic caries detection is going to be doing something a little bit different. So don't take every step here to be exactly how every company does it. But these are just very general ideas. So the first step, just like any other kind of deep learning training, is to get a lot of data. So you need the training data at first. And remember, what is training data? Training data is where you know where the question, the input is, and what the expected output is. So in this case, you need a bunch of radiographs in which you already know has caries or doesn't have caries. The best way to do that is to have a bunch of doctors go through a bunch of radiographs and they mark on those radiographs where the caries are. So in this example, you can see a bite wing, and in this bite wing, a doctor would say the x coordinates and the y coordinates of the caries. Now, there are two numbers in which you actually say that is the position of the caries. That can be used to train the model for finding caries in general. So just so everybody knows, the x and y position, the x position is the distance from the left side, and the y position is the distance from the top side in terms of pixels. So normally they do everything in pixel coordinates, which is one of the reasons why for most of these deep learning image algorithms, they actually have to resize all the images to be the same in order to make the model very consistent. So let's go back to these steps. So step 2, after they create this training set, they have to go through this model and just update it based on the loss. So is it getting the expected output? Just like any other neural network. And then step 3 is you test it. So you give a bunch of real life bite wings or PAs. You may want to give some weird edge cases. Maybe some teeth are missing. And then you get to step 4, in which it is ready for production. And when I say production, ready for the real world. So that's the inference step, in which all you're doing is getting the bite wing or PA into your model and just getting the XY coordinates of where the caries are. Another concept that you are going to be seeing more and more in dentistry is called segmentation. So, generally speaking, in segmentation, you are determining what pixels belong to what. So, this is not necessarily caries detection, but segmentation does definitely help in caries detection. But segmentation says which pixels belong to a tooth, which pixels belong to a crown, which pixels belong to an amalgam, and so on. This is very useful if you want something like a way to automatically do the hard tissue charting when you're doing the exam. So it does most of the work for you. So in this case, it would probably be able to detect that on tooth number 3, there's an occlusal amalgam. Is it an occlusal or occlusal buccal? Well, I guess you'll have to look at the patient's mouth to confirm that. But at least it will mark that there is something on the occlusal of tooth number 3. So you want to have segmentation be an important step for doing other things as well. For example, let's say you actually were able to take a CBCT before the patient's even seated in the chair. And then you had some kind of AI that can do segmentation on the 3D model. So in that case, you would be able to know if that amalgam was just occlusal or occlusal buccal. So there are some tools out there that have started to do this automated segmentation. How accurate it is, I can't really vouch for it one way or another, but I do see this as a potential future, not just in diagnosis, but in overall treatment planning. So you already can see, like, okay, there's a lot of caries. I need to spend a lot of time on this patient versus, okay, I don't see much going on. I can probably do the exam in just 10 minutes. Now, of course, this doesn't replace the doctor in the ability to do diagnosis, but it is can be kind of useful in being able to transfer all of this charting, going through all the different teeth and being able to automatically have it mostly charted, at least get 99% of the work done before you even sit down. And some people are asking how I use AI in my dental practice. Admittedly, I don't use that much AI as of right now. As the disclaimer I had at the very beginning of this lecture, I did write my own dental EHR. Now, the EHR could integrate directly with any AI system out there. It's free and open source, so it could work with whatever automatic caries detection system or whatever segmentation system that's out there, no problem. What I do sometimes, because I don't have a hygienist and I sometimes don't even have a dental assistant, is for periodontal charting. Now, one thing I did not actually go over is the fact that sound is really a series of numbers. So, whenever you record any kind of sound as a file, what it's actually recording is a series of amplitudes, and then that gets stored onto the computer. I mean, it's going to be using some kind of compression to do so, and just like with images, there's lossy and lossless. But at the end of the day, it's a series of numbers. So there is a number of AI tools out there that will convert these amplitudes, which is really sound, into words. So you probably on both your smartphones or other devices have spoken to it. You're probably using Siri or Google Assistant, in which you speak in normal words, and then it'll convert those normal words that you're speaking into actual letters. And then it will actually send those letters to their own system and do whatever it needs to be done. So that's a typical voiced to text AIs that are out there. There's plenty of them out there, but the one that I'm using is called Serper NCNN. As I said before, NCNN can use your whatever GPU you have, either it's AMD, NVIDIA, Intel, and use Vulkan to do the acceleration. And it's really good for inference, which is what I need to do. I'm not going to spend hours upon hours training it with my voice. So what I actually can do is when I'm doing a comprehensive exam, I actually can speak out loud and say like 2, 3, 2, and then it'll chart into the periodontal chart directly 2, 3, 2, and so on. And I just wanted to show this small piece of code because I was using a very generic AI to do this conversion. And because this generic AI doesn't know anything about periodontal charting or anything else, it doesn't know that I'm expecting a number. So I actually put a number of homonyms and group them together to make it such that it will show the proper number when it actually comes out. Because sometimes when you say 2, did I really mean TW or TOO? So I had to write some code specifically for that. There are other software that already does that, but because I knew how to write that kind of software, I just wrote it for myself and I don't have to pay for any kind of licensing fee. But that's the end of the lecture. I really hope you enjoyed it, and I consider this more of a part one of a series of lectures, and I would like your feedback on what would part two be. So one idea is having a lecture on how to train the models further for your specific use case. For example, in that previous example of me having to take into account TWO, TOO, three, sometimes it came out as tree. How would you do that in your own practice? That could be one lecture. Another lecture could be just a basic intro to Python. As I mentioned earlier, all these frameworks like to use Python for everything. And if you know Python, you can get started. Now, this is not going to be an entire computer science course. This would be just an introduction to Python just to get you started. A third idea would be on building your own website. So this would go over how to register a domain, step by steps, how to make your own website, and also how do you do your own SEO? So, how does Google Ads work? How does Facebook ads work? How do you know which ones are being effective, which ones are not being effective? And then the last idea I had was just a general introduction in digital video and digital image software. So the idea is that you have your own practice, you want to make your own YouTube videos, or you want to post something on TikTok. The editors there are not going to get everything done for you. So this would be just using free and open tools that you can use to make your own promotional videos and images. So any of those ideas, or if you have any other topic that you'd like me to go into, I'm definitely open to that. And I thank you for going through this long course. I hope the math didn't bother you too much, and have a great rest of the day.